So, good morning or good afternoon, depending on where you're joining us from, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those who don't know, we are all about bringing conservation, adventure, and science into classrooms around the world. Today is part of actually the beginning of our entire month dedicated to space and space exploration. So, all month long, we're going to be having amazing people talking about the stars, the planets, how we can learn more about the Earth from what we're doing in space. It's going to be a really fun month. So right now we've got two classes from across North America joining us. I'll give them a chance to do a bit of a shout out. We've got Miss Custer's grade 5 in Little Rock, Arkansas. Hi, guys.
Hi.
And we've got Miss Grimshaw's grade 5s in Freehold, New Jersey. Hi, guys.
Hi.
Awesome. Of course, the reason you guys are all here is for our speaker. So we are joined live in London, Ontario, Canada, by Dr. Parshati Patel. She is an astrophysicist and science communicator. She does work all over Ontario in science communication and is a really frequent contributor of ours. She is the outreach coordinator at the Center for Planetary Science and Exploration, a marvelous organization. And so without further ado, I'll leave it to her and take it away, Dr. Patel.
Thank you. Hi, everyone. I'm really excited to talk to you guys about my journey as an astrophysicist and now as a science communicator. So to start off, I'm going to talk a little bit about my research. First of all, how I got inspired to be, an astrophysicist. About a little bit about my research, and then what I actually do in terms of my everyday life when it comes to a researcher, and then when it comes to a science communicator. A lot of students have recently actually asked me, oh, what do you do? What does an astrophysicist do? Like, do they just look at stars in the night sky, or what is it to be an astrophysicist? And so that's actually gave me an inspiration to come up with this presentation where I'm talking about my research, but I'm also talking about what it takes to do that research. Okay. All right. So I'm going to start my presentation right here. All right. So I'm going to start. Oops.
Nope.
Did it go through?
No, not yet. Still you.
Oh, okay.
It wants to.
Okay. Always something that goes on with this.
Tech difficulties are for. There you go.
Okay.
I'll let you know when it's actually fully up, okay?
Okay, perfect.
And you're good to go.
Awesome. Okay. All right. Okay. So finally, so today I'm going to be talking about stars, disks, and classrooms, and the title is kind of inspired from all the aspects of my life on everyday life has been for the last at least 6 to 7 years. To start off, I was born and brought up in India, and I always wanted to learn about things around me. But I did not know much about stars until I actually went to a planetarium in the city of Mumbai, which is right here. And it was a vacation. We were just there to kind of learn about things and kind of enjoy our vacation. But when I looked, when I sat through the show for the planetarium, I just had more questions. What are stars? What are planets? And my parents, they aren't from science background, in space background. So what they did was they just bought me books. And, I asked a question, what are stars? And they would buy me a book on stars. I would ask, what are galaxies and how was the universe born? And like those simple questions. And they would just keep on buying books for me. Couple of years later, my aunt learned that, I keep asking for astronomy books all the time. So she bought me a telescope, something like this one. It was very small, not really big telescope like you would find in observatories or anything like that. Just a small handheld one that I could, use with a tripod. And through the telescope, I was actually able to look at planets like Jupiter and Saturn, Moon, and Pleiades, constellation, things like that. When I looked at the moon for the first time using the telescope, I realized that this is such a cool thing to learn about. Like, I would want to do this for my life, like my living. I would want to know how these things formed and what made it form a certain way. Are there other exoplanets outside our solar system? Is there life in the universe? All these burning questions I had. As I was growing up in high school, I learned that, I need to take physics and astronomy or physics and math in order to get into astronomy. So I was actually able to take those courses, keep my love for astronomy going as I understood more about physics and math. And then I got an opportunity to come to Canada to study astronomy, and ever since then I have kind of kept my path into astronomy, but also expanded into planetary science and space exploration, which I'll talk a little bit about later in the presentation. So when I came to do my PhD, I was really intrigued by how things form, whether it be planets, stars, galaxies, or the universe. And I was in particular very much interested in how stars form. So here is an image of Orion Nebula, which is one of my favorite nebulas to look at. It's really pretty and beautiful. All of these dots that you are seeing are actually massive stars that have formed. These regions contain the ingredients that we say that forms stars. So everything such as hot gas, hot dust, massive stars that are almost exploding, basically sending out waves of energy to the rest of the star forming region, and that kind of triggers more star formation. And so when I was doing my PhD, I realized that it would be really cool to study very, very young stars. And so I picked a lot of the stars in this region to study. But when you want to study these stars, there are always things, obviously, due to technology, that we are not able to actually directly see these stars. What we are able to still gather, thanks to the Hubble telescope, are these faint images of what a star, when it's forming, looks like. So, for example, let's look at the one right here. What you're seeing is like the side shot of a star that is surrounded by a lot of dust and gas. Over here, you are seeing the star is being formed, but there's a lot of dust and gas that is being blown away. Same here. All of these are actually images of real stars that are forming right now, and Hubble was actually able to take around 200 images of this Orion Nebula, and they called these, young star-forming disks as Proplyds, or protoplanetary disks. And you can see they come in a variety of shapes and sizes. So some here don't have any kind of tails. Some have these massive amount of gas that is blowing away from the star due to the wind. So you have tails that are coming off of the star. Sometimes you just have a giant blob of gas and dust surrounded by it, hardly letting you see what's actually happening inside. Okay, so when we look at these stars, so let's go back to the image we had originally. So in this image, other than the squares that we have shown, you can see that there are stars of different colors. So you have white ones, you have orange ones. Depending on their mass and temperature, you can get different colored stars. So for example, G-type star, our sun is a G-type star, so it's very yellow when we look at it. But as you go and look at more massive stars, they're more hotter. They're bigger and more hotter, so they are more white. It's just like looking at a candle, but closer the wick you get, the more bluer or whitish blue you get. And that's exactly what the color of these stars are. So you start from red, you go all the way to the white. And there's a massive range of temperatures and masses when it comes to these stars. So they can range anywhere from 3,000 degrees to 30,000. To put in context, our oven is around 400 to 450 degrees Celsius, which we put in a pizza. And compared to that, these stars are very, very hot. I mean, the most massive stars could be 30, 40, 50,000 degrees just on the surface. Okay? And they range in sizes a lot as well. We can find, stars that are 1/10 the size of our sun, but also maybe 60 times the mass of our sun. So they could range in a variety of sizes and temperatures. The ones that I particularly like to study were the O and B type stars, so the most massive stars. And one of the reasons for that is a star like our sun can actually live a very long life compared to the star like maybe a B type star. And so because the B and O type stars, they evolve really fast, they get from the baby phase to their end of the life cycle really, really quickly compared to a star that is maybe M or K type. So understanding how they form is very important, especially because when they're forming, so I'm just giving you a sample of, one of the stars. When you're looking at these young stars, they're surrounded by disk and gas, and you're not really able to see what's happening to the star itself. We do see, the amount of light from it. So obviously something is happening in there that's generating a lot of heat and a lot of light, but we cannot directly see it. So we have to infer it in many different ways, what's happening in there without actually seeing inside. So it's almost like listening to a room, actually standing outside the room, the door is closed, but just listening to it and trying to figure out what's going on in there. And the way we like to do this, and before even I go to the actual how we do it, just imagine if you were able to slice this star and the disk into half. What you would see is there's a small star in the center, which is just forming. Because it is so hot close to the star, all the dust evaporates. Okay, so you get a region of just gas around it. And then as you go further away, you keep getting more dust, and this dust is the material where all the planets form. So they are, they start from very, very small grain-sized things to boulders, which eventually will coalesce to form planets. Now, when I'm looking at these objects, I obviously need some kind of technology to listen to them. And one way to do that is actually see what's going on in there without actually seeing. And I'll show you in the next slide what I mean by that. But I get to use big telescopes like the Canada-France-Hawaii telescope to look at these stars. And there is an entire process of competitive process where you compete with other people from around the world for time on this telescope. And so a lot of my time is actually spent in writing these proposals, getting time on these telescopes and getting data from them. And this is just one of the examples. There are very many telescopes around the world that people use to study stars. Now, when I collect light or data, as I say, from these telescopes, what I do see is something like this. So every one of you would have seen a rainbow, right? That is light splitting into these colors. That's the same kind of light I use to study these stars. Now, you are seeing right here on the screen anything that goes from purple to red. All of these are just star numbers, so don't worry about them. Something to concentrate on is all these lines. You're seeing these dark lines. Some of these are bright. Most of them are dark. All of these lines are almost like fingerprints. These are fingerprints of elements that are contained in this cloud of gas as well as the star itself. So if I can decipher what these lines are, and if I can understand and recreate these lines, I could actually tell what's around the star and where in the disk or close to the star or on the star itself it is. So it's a very important piece of information that this just a slit of light is actually giving me. So what I do in my day-to-day life is actually take this data and I create a computer model. So in my computer, I create a star. Here's an example of that. Here's a star. I create a star of whatever mass, temperature, size that I would like. And then I create a disk around it. I know what kind of gas it requires, what amount it requires, what amount of dust it requires, and how big the disk may be. And based on those things, I recreate a star and a disk in my computer. Now I take the data that I have, and then I recreate a star. Now my last kind of job in this entire process is to actually compare the two. So I take the observations, and then I take the computer simulation or computer model that I created, and then I compare the two to see how right is my computer model, how accurate is it to what is actually happening in real life. And when I compare the two, I actually can understand what is the disk geometry. How does the disk look like? If I were to travel there, what would it look like? How would it feel? Is it very dense? Does it have a lot of material? Does it have little gas, a lot of dust, or the combination of the two? And that is something, it's very simple. You're comparing two different things and you're modifying your model based on what you think is happening to the disk. And we understand the basic physics really well in order to be able to do that. So if you were me what are all the things you're doing on day-to-day basis. So I'm writing these observing proposals that I talked about before, where I'm competing with other people for time on these telescopes so I could get the data I need from these stars. I'm coding the computer models, an image of which I showed you. Once I do get the data, I do have to do a lot of, cleaning the data, because there's a lot of part of the data that I don't really need, or sometimes you have a lot of noise in the background noise that you want to get rid of. And then obviously you want to analyze and make sure that data contains the kind of those lines that I showed you, or the fingerprints of these elements that I'm really looking for. And once I have that, I compare, find my results, and obviously have to write it into a paper so that other people who are in my field are able to actually read those papers and understand where we are going in the direction in terms of research. Sometimes I also get to attend conferences. This is where I present my research and tell the world, this is what I did and this is what I found. But also reading other people's work is equally important when you attend conferences, learning about what other people are doing and how that might have impact on the kind of research I do. So that is kind of in a nutshell what a life of an astrophysicist would look like on day-to-day basis. Now, 2 years ago, I graduated with my Ph.D. and I directly moved into, something that was a little bit beyond astronomy research. So I always loved talking about space and how important space is to us, and why we should be curious. And I wanted to, show that passion, show how important astronomy is to everyone. And so I joined CPSX, or the Center for Planetary Science and Exploration, as a science communicator and educator. So for that, what I do is on day-to-day basis, I'm going to classrooms, doing something like what I'm doing right now, talking to students, talking to them about space on a variety of topics, not just astronomy, but also things like space exploration, planetary science. I'm talking about the next generation of astronauts, all of these different topics that involve anything that involves space. We're talking about that in classrooms. I'm also really excited to say that I get to lead the Space Explorers Camp here in Southwestern Ontario, where we bring kids who are really liking any aspect of space and bring them over on the summer, have a full week of awesome space-themed activities. We also get to do a lot of public events. We have an observatory here on the campus, and we collaborate a lot with them to bring not only students like you, but also adults to have a look at the telescope, look through a telescope, understand more about the history of astronomy, and a variety of different topics such as moon, including lots of different national and international campaigns that run in Canada and around the world. And then last but not least, I also get to lead a podcast, which is called Western Roll. So my role involves a lot of different aspects of, doing science outreach. And so on day-to-day basis, what you would see me doing is leading workshops, developing activities and programs, all space-themed, organizing massive events, but also at the same time conducting research and analysis based on the kinds of programs we develop. It also involves a lot of social media and promotions. So, talking to public over Twitter, Instagram, Facebook, and then obviously managing a lot of people that work under me. So these are two different aspects of scientists that a lot of people like to get engaged in, whether it's the science itself or actually communicating the science. So I'm hoping you got a little bit of taste of what it would look like for an astronomer / science communicator to be doing on things that a person would do on an everyday basis. All right, so I'm ready to take questions. Hopefully you guys enjoyed.
Thank you so much, Parshati. As you're getting your screen share off, I will start with the Custer's group. If you guys have a question, come on up.
Yes, I think so. Guys, who has a question? Tanner, how small can stars be?
So 1/10 the size of the sun is kind of the lower limit of what a star could be. There is a very fine distinction between stars and planets. So kind of the definition that defines them is a planet does not generate its own energy using nuclear fusion, while a sun or a star would. Okay, and so that 1/10 is kind of the size where we think it kind of cuts off and becomes a planet. Anything smaller than that would be a planet. Anything bigger than that would be a star.
So basically, once something gets big enough, it becomes like a giant nuclear bomb, constantly going. Kind of way of looking at it. Okay. All right, let's go to Miss Grimshaw's group. You guys have a question? Everybody has a question.
We have a lot of questions here. We're going to try to get to it. Here we go.
Is there layers of stars? Is there layers of stars? If so, how many?
Yes. So depending on the size of the star, the layers change. So if you have ever had a chance to look at the sun through a solar telescope, you would see that it looks like it's almost shooting material out of it. They're sometimes called flares. That layer is a convective layer. So if you guys have learned convection in your school, you would know that that's the material that's coming out. So that's the top layer. Inside our sun, you get where things are radiating. So that's the radiative layer that's inside. But based on the size and the mass of the sun, the more hotter it gets, the layers change. So for example, the stars that I study, they actually don't have that convective layer that our sun does. That convective layer is actually right in the center of that star because it's so massive. The amount of energy it has to radiate away is a lot. So all the top layers are radiative layer. And so there's, depending on the size of star, you would get different layers at different, sizes from the center to the top area.
And is there a maximum? Is there like 4 or 5 separate layers within a star? Is there a core to stars? Or I mean,
we generally say 3 is generally, so you have the core and then you have 1 layer and 2. But certainly, depending if you are studying the core and the layers itself, you would divide them in more, separate names. But generally, people who study the outer part and the rest of the star, we only say 3 layers: the core and radiative and convective layer.
Perfect. All right, for the classes, all the kids that had questions, we have lots of time with 2 classes here for questions, so we're just going to alternate between the classes and give you guys lots of opportunity. For now, we'll go back to Ms. Custer's group. Give it a second question.
How hot can a star get?
How hot can a star get? So on the surface, I showed you guys the picture of the most massive stars. On the surface, it could get anywhere from 30 to 40 to 50,000 degrees. At the core, in the center of a star, it could be millions of degrees. So, for something like our sun, 1.5, 2 million degrees in the core. On the surface, ranges anywhere from 3,000 to 60,000 degrees, depending on where it is in its lifetime. So yeah, they can get pretty hot.
Now you compared it to an oven in your talk. What is it compared to something like lava or like the hottest thing people can imagine on Earth? Is it hotter than that? Is it as hot?
Oh, definitely. I like to use the oven just because everyone can visualize how hot it is when you open the oven and you can feel that warmth on your skin. Imagining 50, 60,000 degrees, it's very hard. You can just think maybe it's 10 times, 100 times more hotter than your oven.
So you would just, if you were beside the sun, you would just like vaporize. You would turn into ash, basically.
Yep.
Okay. Cool. Let's go back to Ms. Grimshaw's group.
Have you ever seen a shooting star? Where?
Yep, I have actually seen tons of them. Sometimes over the summer when we know that there is going to be a meteor shower. So just to make sure that everyone is on the same page. So shooting star is also a meteor. So the more common name is shooting star. Meteor is when you have these small tiny particles that come through the atmosphere and they burn up, and it looks like it's almost like a streak of light. Sometimes you do get bigger objects and you get a giant fireball. I was lucky enough to be throughout many summers to actually be able to go out and camp during these meteor showers. So I can, just see these. And so I would count, I have seen, I think, up to 80 meteors per hour, which is pretty brilliant. and I have seen quite a few fireballs as well. And so certain times of the year, you do get these meteor showers. And if you guys have a chance, you should certainly go out, go to a dark sky area, bring sweaters, a little bit hot chocolate with you, and just gaze at the night sky and see these shooting stars.
Very cool. So yeah, the key is just to get out of the city, is to leave areas where there's lots of light, because when there's light, you won't be able to see anything.
Oh yeah, and also got to tend to keep our eyes away from any kind of electronics as well. It takes at least 30 minutes for our eyes to adapt to the darkness. And so, if you go out, stay at least for a couple of hours, the more longer you stay, the more of the shooting stars you'll be able to see.
Excellent. All right, let's go back to Miss Custer's group.
Hayden, how far away is a star from Earth?
So the closest star, obviously other than our sun, the closest star is 4 light years away. So what do I mean by 4 light years? It's actually a unit of distance. So if I were to travel at a speed of light, this is a constant speed. It's super fast. We have not been able to actually reach that speed with any of the technology that we currently have. If we were to even be able to create that kind of technology and travel at the speed of light, it would take us 4 years to get there. So it's super, super far, okay? That's the closest one. And beyond that, you just keep going, okay? So yeah, 4 light years.
And how close is the sun to us? Because it's our closest star, how far is the sun?
So that's 8 light minutes. So any light that you see from the sun, so the first light that you see in the morning has actually left the sun 8 minutes before you are actually able to see it.
Very cool. So the speed of light, just for the classes to understand, but there's an analogy I like here. It's 300,000 kilometers per second?
Yep.
Okay, so in 1 second, a beam of light would go around the Earth about 8 times. So it takes 4 years to get to the nearest star if you can go around the Earth 8 times in 1 second. So that's a really,
Yeah, I like that one.
Very fast. It's very far away. All right, let's go to Miss Grimshaw's group.
Ready, go ahead.
What was the most unusual event that you've seen happen in the solar system?
Unusual event that I would say I wouldn't say that I've seen it myself. I've seen it in pictures, which one thing that I find really intriguing is that I think it was during 90s, if I'm not wrong. So all the planets get hit by asteroids or small rocks. And Jupiter got hit by one of these rocks. And over a period of time, as you guys know, Jupiter is a gas giant, right? So even if it hits Jupiter, it's actually just going through its clouds. And they were able to track that disruption in the cloud over months. And I thought that was pretty interesting because here on Earth, if you just get hit by a rock, there's a giant hole in the ground, and then it just, over time, basically based on, erosion from wind, water, or it gets filled in by snow, you are not able to see any of that. But we were able to track this for months on Jupiter, and you could see how that hole was really big when the rock went through, and then it went smaller and smaller over time. So it was pretty cool that I could see that in pictures. I haven't really been able to watch any kind of event other than the fireballs that I mentioned with my eye. I mean, I have seen planets and obviously some of the Jupiter's, so the Galilean moons actually going in front of Jupiter. That's another thing which I've seen through a telescope actually happening. That one is pretty cool too, but I really like looking in the pictures, that giant hole that shrunk over time.
One other thing, I don't know if you got a chance to see this actually in its totality. So one astronomical phenomenon you can see on Earth is a total solar eclipse. I don't know if you went down for it, and I don't know if the classes were actually right in the path. It probably would have been just off it, but
I was just off it. So we weren't able to see it here in London because it was raining and it was cloudy. When I was young, I think it was early 90s, when I was probably, 10, 12 years old, there was an eclipse back home. And obviously in India, there is a superstition that you don't really look at eclipses. So everyone told me not to look at it, but I was a rebel because I love science. So I went onto my terrace. I had eclipse glasses with me. and I looked through the eclipse. I thought it was a total eclipse because it was almost covered. Only a couple of years later, I figured out it was only 99%, so I missed by like 1%.
Right. That's an amazing thing. We actually have several of our speakers over the next month to talk about chasing eclipses all over the world. So it's a lot of fun, and I hope the kids got a chance to see at least a partial one this past year. Yeah. All right, let's go back to Miss Custer's group.
How long does it take a star to grow?
How long does it take for a star to grow? It all depends on its size. So for something like our sun, it would take millions of years. For the stars that I study, they would grow really fast because they're really big, and they basically burn through their fuel really fast. It would be somewhere around 100,000 years to, closer to a little bit less than a million years. And again, depending on the mass, the more massive you are, the faster you're going to burn through your fuel, the faster you're going to go to the kind of phase that the sun is in, and the faster you're going to die. So yeah, anywhere from, a few thousand years to a few 100,000 years, depending on your mass for massive stars.
Very cool. All right, Ms. Grimshaw's group. We are whipping through so many questions here. I love it.
Yeah.
Is the gas around the stars a dangerous gas to breathe in?
Ooh.
No, so it's actually, it's a mixture of a lot of material, mainly hydrogen and helium. I would certainly not suggest, humans to wander out in that, but it's not toxic in a way that, it would harm us. Certainly we humans cannot breathe in space, but if you were to look at the composition of the gas, it has all the ingredients which planets here in the solar system are made of. So, for example, Jupiter is a gas giant. All that gas that you see in its atmosphere, all that is actually, the planet itself was created from this gas that was available when the planets were forming. So all the gas and dust that we see around other stars are similar to what was around when Earth and the other planets here in the solar system were forming.
Yeah. I don't know, by show of hands in the classes, has anyone ever taken a helium balloon and sucked in and then your voice gets really high? Like one kid's hand just shot up so fast there. That's awesome. So maybe, okay, other than getting incinerated into ash, if you went near the sun, maybe that's the effect you'd get. It'd be kind of fun.
Yeah.
Right. Let's go to Miss Custer's group. Let's do like 4 more questions, guys, and then we'll wrap up there.
Callie.
Earlier you mentioned a fireball. What is a fireball?
So fireball, so meteor shooting stars are generally very, very thin, tiny objects that are going through the sky. They're burning up, and halfway through, almost through the sky, you would see they disappear. That's because they completely burn up. They're very, very tiny, sand-grained kind of material. When I talk about fireball, they're actually bigger. They could be size of a small rock to sometimes actually also be, big, giant boulders. If you guys, I don't know if you guys had a chance to look at the 2013 Chelyabinsk meteor, but that one was a giant, almost school bus size object that came through the atmosphere, burned up most of it, and the leftover material was around, I think, 500 kilograms. So you could have a rock that is the size of a school bus that goes through the atmosphere, burns up really bright, so you're able to actually see it even sometimes in daytime. And that kind of really big object, you would call it a fireball. Okay, and most of the time, because these materials that are coming through the shooting star or a meteor and these giant fireballs, they're generally part of either the comet leftover material that goes around the solar system, or it could be the small asteroids or small rocks from the asteroid belt that are coming towards Earth. Okay, so yeah, when they're a little bit bigger than the size of a small rock or anything bigger than that, they generally create a really bright light in the night sky that, even if your friend saw it and be like, oh my God, I saw it, and you turn around, you're still actually able to see it. Generally, when it's a shooting star, it's like, oh, I saw one there. By the time you turn around, you'll probably not be able to see it. The shooting stars are so quick. Fireballs are longer and more brighter, so you're able to see it for a little bit longer time.
So when we're done this hangout too, I'll pass along a link to both classes where they can see the Russian fireball a couple of years ago. It was amazing. Just your reference to the classes, you're talking about things from sand grain size to maybe like a football to maybe even a school bus. How big was the one that wiped out the dinosaurs by comparison?
It was around a few kilometers in size, a few tens of kilometers in size.
A mountain coming in.
Yeah, yeah.
Cool. All right, let's go back to Miss Grimshaw's class. While you're coming up, can I just say I love how enthusiastic both your classes are. Like everyone has so many questions. This is great. So well done to both teachers. Okay, go ahead.
Can you tell patterns from the stars?
Sorry, what was your question again?
Can you tell patterns from the stars?
Do you mean like constellations?
Yeah.
Yeah, so constellations, generally, when we look at the night sky, at least from our perspective here on Earth, we see certain bright stars and, certain lighter ones, and we generally create, while human brains has a thing that, when you're constantly looking at something, you start to create patterns in it. And that's how, when you're looking at the night sky, you see a lot of these different constellations, and they have certain shapes, and obviously there are stories related to it now. But we do, when we look at these stars, we generally don't see much because we're actually individually looking at single stars. And so when we are looking at these stars, you only get light from this one object. So we're not really seeing any patterns. But in the night sky, when we do look up, we certainly do we do analyze in a way that we're looking at patterns, and we feel like we're seeing something that looks like a bear, something that looks like, maybe a Pleiades constellation. And that's just our brains kind of tricking us almost to think that way.
So just to confirm, so these stars aren't actually like in the same level away from us. They're way distant apart, and we're just making it up with our minds? Okay.
Yeah, it's just our perspective from here. That's how they look like.
Cool. All right, we'll take one more question from each class. We'll start in Miss Custer's group. Ooh, who to pick?
Cole.
Do you know anyone that's gone to space?
Do I know anyone that's on the space? Well, I know an astronaut. I worked with him very recently. He has been to, he's a Canadian astronaut called Dr. Dave Williams. He has been to the International Space Station. He has the record. I think he's the record holder for the longest in total Canadian spacewalk that he has done. And I recently worked with him on his book. He's now an author. He writes books, and I worked with him on his book, so I know him kind of personally.
Very cool. So Dr. Dave Williams actually has quite a few children's books now, so I can also pass along links to those if you guys are interested in learning more from the perspective of someone who's been up there. We also have a hangout, I think, in 2 weeks or a week and a half. There you go, one of the books.
I have the book, Destination Space.
Yeah. We have a hangout with an astronaut who's been to space in about a week and a half named Terry Vert. So if you're interested in that, you can always watch on YouTube as well. Cool. All right, let's go last but not least to Ms. Grimshaw's class one more time.
How many stars did he study?
How many stars did I study? So I actually studied 4 stars for my thesis. So it looks like a very small amount, but it takes a lot of time and data and computational power to do that. I do have additional 6 stars in my database that I'm yet to study. So in total, I would say 10 stars. So the 6 stars that I'm talking about are the ones that I acquired the data myself with this competitive proposals that we write for these telescopes. And yeah, but I was only able to get through 4 of them out of the 10 during my 4 years of PhD.
Okay. Well, before we wrap up, Dr. Patel, is there any last message you want to share with kids who might want to learn more about space, where they can go, what they should do in school, and anything like that?
Yeah, I hope you guys were curious from all the things that I told you about the stars, but there's so much more in terms of space, whether it being becoming the next astronaut to, creating new technologies that will then advance us to understand the stars and the galaxies and how the universe formed. So I hope you guys stay curious and feel free to email me if you want to, if you have questions. I'm more than happy to answer them. And just be curious and look up a lot of, authors that talk a lot about space and just get intrigued by it.
Cool. All right. I'll be sure to pass on your email to the classes as well so they can follow up. But for now, as you know, at the end of every hangout, so I'm going to demute both classes, so Ms. Custer's class and Ms. Grimshaw's class. If you guys could join me in saying a big thank you to Dr. Patel for joining us today. Thank you so much. For the classes, we've got tons more Hangouts on space all month long, and of course, Hangouts on all manner of sciences all year. So please do join us again soon. Dr. Patel, thanks so much for joining us today, and we look forward to having you back soon.
Thank you.